All right, thank you. This is my first trip to Toronto, and most of my time at Yelp I've spent in San Francisco cheering on the Golden State Warriors. I don't know if you all are any basketball fans, but a couple years ago they traveled to Toronto, and it didn't turn out so well. Broke my heart. I'm going to hand it off to Rajvinder, who's going to speak about the kind of how we organize the ML platform teams, and then I'll come back and talk about implementation details.
Cool. Thank you so much, Ryan. So before we kick things off, just wanted to get a sense of who might have heard of Yelp. So please raise your hand if you've heard of the product. Cool. So that sounds like it's most, if not all, of the room. And so this might be a recap for some of y'all, but Yelp's mission is to connect people with great local businesses. And to give you a sense of the scale that we're operating at, in 2021, we had 33 million monthly unique visitors, 244 million reviews, and 5.8 million active claimed local businesses as of the end of last year. And yeah, before we kick things off and dig into the ML workflows, like how many models do y'all think exist within Yelp? And so if y'all think it's less than 50, I'd love for you to raise your hands. Okay, 0 hands. If y'all think it's less than 100, would y'all raise your hands? Okay, got some hands. But if you didn't raise your hands, you're right, because there's over 100 machine learning models in production at Yelp. And so, with these models, we power lots of key critical user experiences, such as our home screen recommendations, where we've got multiple models powering all these experiences that you might see behind you, to ads and search ranking, where our machine learning models help surface relevant businesses along your user shopping journey and help connect you to great local businesses. And once you've connected and made a reservation, we help to estimate for wait time estimates. And so you might get a sense of how long of a wait there might be and how to plan the rest of your evening. And once you've arrived at that local business, we help you in your decision-making process and your shopping journey there as well. And so for the agenda of today's talk, we want to give you an overview of our ML platform, the tech stack that supports our ML platform, and challenges for adding paved roads for Tensorflow. We'll be going over implementation details and the projects that are needed to accomplish this goal. And what we hope you can take away is understanding the challenges and what you might need to implement neural networks in low-latency inference applications. All right, to dive in, the ML platform team's mission is to empower Yelp-wide usage of machine learning and data mining to solve impactful problems for the business. And so from a technical perspective, we're building and supporting common ML infrastructure and data mining tooling that's used throughout Yelp. From an outreach perspective, we're identifying and aiding in the development of data mining and ML projects. And from an education perspective, we're empowering ML usage throughout Yelp with awareness and education initiatives. And so the illustration on the right gives you a sense of how we view our teams and how they layer up to deliver business value. And so from our ML compute teams and tooling, that layer up into data and feature stores teams and tooling, which layers up into our model platform teams and tooling, and then ultimately the ML modeling teams. Throughout these layers and teams, we support customers to proactive ML outreach to ultimately deliver business value to customers such as search, ads, trust and safety, and restaurants. So this is a picture of our ML workflow. It might seem pretty familiar to y'all, but we help our customers throughout this entire process. And so customers might start with an exploratory idea or a set of features or modeling techniques they might want to try. So they'll first start in our ad hoc compute platform with their centralized Jupyter Hub, iterate through these different ideas that they have. Eventually, once they've got an idea of the data pipelines or feature pipelines they'd like to construct, they might move over to our data ETL infrastructure. And so they might use Spark to build data pipelines or feature pipelines and publish them into our centralized feature stores. Afterwards, they might use our model trainer and model trainer libraries to train their models using Spark and eventually deploy these models using our model server library. So really, we view each of these steps as very iterative, and so we measure success through the number of ML workflows that people are able to iterate along each step in this process. And we really have a keen eye towards understanding and supporting the model retraining lifecycle throughout using CI/CD tooling as well. And so for the ML platform tech stack, like we just discussed, Data modeling and prototyping is done within Jupyter. And our centralized Jupyter Hub has integrations with our internal ML compute platform. It's just Kubernetes and Spark. And our model training compute workflows are in Spark as well. But the interesting thing here is that our batch training workflows and the feature transforms conducted within them are done through a centralized library called MLeap, and which we've spoken about before at this conference. And our ML training metadata is cataloged within MLflow. For model serving and deployment, MLeap is portable to many JVM environments, and so we've got folks using our model inference and model server through microservices, Apache Flink, and even within Elasticsearch. And we support all low latency ML applications using this tooling, and including all production search traffic. So earlier this year, we had a really interesting question, which was how should we think about the investment for paved roads for TensorFlow in our ML platform? And so we don't take these investment decisions lightly. We really wanted to make sure that we were thinking through the investment through a really customer-centric lens. And so the fact that low latency TensorFlow model inference wasn't supported in our platform was actually a blocker for our customers. And so many folks actually internally told us that they weren't seriously considering applying neural networks to key business problems because there just wasn't a path to production. And so we had that customer feedback in hand. And the other things that we had were that an exploratory prototype had showed incredibly promising results with neural networks as well for a key business problem. Embeddings were becoming more popular internally as well, and were actually becoming more important features for other use cases. And we knew that there was a lot of customer demand to utilize larger data sets and more representation learning techniques, and neural networks were a good way to do that. And lastly, we were really confident in our serving infrastructure because we were able to prove that we could run production level traffic with our MLeap pipelines and ensure that there was low latency model serving within XGboost, with XGboost. And so with all those factors and confluence of knowledge that we had about our internal business case, we were able to make a decision to invest in the platform. But once we made that decision, there were actually lots of challenges that came across the way that Ryan's going to dig into. But super quick, from a compute perspective, how could we ensure that we could enable rapid iteration with our neural network libraries that we wanted to enable internally? We know that they're GPU hungry, or would we be able to support that in our ML compute stack? From a data and features perspective, what data support will we need to ensure that we could have rapid iteration on our embedding features and have that prototyping cycle be relatively quick and make sure that there was no developer toil there? From a model platform perspective, like we talked about, how can we enable TensorFlow for inference in our MLeap and our model inference package? And how can we deploy this in our native search engine? And lastly, how can we best enable our customers to use these embeddings and model architectures given the challenges for real-time ranking problems? So with that, I'm going to hand it over to Ryan, and he can walk us through the next part.
Thank you, Robin. I'm going to share with you the collection of projects that we took on in the last year to accomplish the goal of low latency model serving using neural networks. And I really hope that this motivates you to try out this type of application, and hopefully we can show you how you could decompose this type of problem into several little projects that you can progress iteratively, and then there's some cool tricks and tips that in case you get blocked, you might be able to try one of these tricks that we've discovered. Breaking down these projects kind of from start to finish on the prototyping, training, inference, and deployment. Now first, as Rajvinder mentioned, we had a prototyping model where we had to figure out what type of ML model and architecture we should try that would work. With these models that run online, you don't really know how well they're going to perform online until you serve them with production traffic and get the feedback of what happens when you serve the ML model. You can't really know how it's going to work online until you build all the infrastructure out to make it work. So you have to have some sort of proxy metric to compare the status quo. And so we rigorously figured out some proxy metrics to figure out for our business use case of ranking businesses, which metrics to try to make sure that we're picking the right model architecture. One of the other key components is embeddings, and it's a big theme throughout here. But on the model architecture itself, this was one of the leading candidates. It's what is commonly known as like a wide and deep model. The wide part has a lot of standard kind of numerical features, other features that were input to the XGboost model that is in status quo. And then more on the left, more embeddings types of features. We have a lot of pre-trained business embeddings that we use as part of this, and also train some categorical embeddings for like business category. Because we're not just restaurants, we have services and different types of services like dentists, plumbers, that kind of thing. Okay, so embeddings, we need to figure out how to look them up in training and prototyping. This actually takes a long time. We noticed that a lot of the computation was being pushed to the CPUs, and so this is the first hint that we should actually explore which different types of instances we should try here. And you know, we did move to a newer version of Tensorflow that like mitigated this, because some of the like in a more modern version of Tensorflow, the lookups can be done on GPUs, but still we found other reasons to try out CPUs, which we'll talk a little bit more, and I'll share more on embeddings in a little bit. Another interesting reflection is that a lot of the traditional deep learning models are on text and photos. A lot of the talks here are on foundation models as well. And these types of models are, the data blocks are really large, so like think of like a photo, and these require pretty deep, complex networks. For our problem, we had a lot of smaller data features, littler data blocks, and so there's less computing per block. And so this led to us exploring the path of actually using more cores than like a traditional GPU-heavy problem. So how do we get those data blocks into the TensorFlow network? Initially, we tried Petastorm. It's a natural choice. It works. We noticed that it still wasn't very fast. Our training per epoch was taking like 1 to 2 days. And so we tried Arrow.io and noticed that it had some really nice features of prefetching data a bit better than Petastorm. And for our use case, this sped up the training time per epoch for about 20 times. And this goes into a little bit more detail of that approach. So basically on the left, we're using Spark to extract the data and put it into like a Spark data frame. And our model training Python package actually forks an Arrow stream server that runs and fetches the data blocks. And then it actually communicates to the C part of the TensorFlow graph using socket programming or socket APIs, so it doesn't have to go into the Python layer like Petastorm. Another thing we looked at is different types of instances. So incorporating, exploring GPUs, CPUs, and T4s, we found some more speedups. We tried GPUs, of course, at first. This makes sense, but we actually found that there's a lot of downloading, uncompressing, decoding of all these little data blocks. That when we moved to a large CPU box, we got like a 25% speed up. But then we tried further to the T4-based architecture. It has more GPU type capabilities. It's more balanced. It has 16 cores. And notice that this actually led up to a 4x speed up. It's also cheaper and less energy. And so, these timings here actually comprise all of the speedups that we tried in the previous slides. So it was more like 1 to 2 days per epoch down to 30 minutes per epoch if you kind of zoom out the whole project, which is pretty mind-blowing. Okay, so now we're on to model inference. We have this model trained. How are we planning to serve it in our deployment, inference and deployment? Rajvinder mentioned MLeap, and wanted to cover a bit about what this tool does, and it's the key to our ML platform. It is a model training and serving inference engine. And a key part is that it stores feature transforms, so like variable normalization or handling nulls or things like that with the model binary, so that you can use the same code in training and in serving. And of course, you all know that this reduces a source of error where we've had teams like implement normalization in Python and then the serving environment have to implement it in Java, and it's different. They handle nulls differently, and so even like the floating point accuracy has led to changes. So having this is the same code being used in model training and serving is a really key part. And storing that with the model binary is a key enabler here. It's also a very fast inference engine. Okay, so for our use case, it didn't really work for MLeap TensorFlow. We had to build some Python bindings for it. We needed to figure out like which TensorFlow APIs we wanted to use and kind of port through the bindings. Another common theme if you're using MLeap is that it has a common set of feature transforms, but what we found is that a lot of our customers internally want custom feature transforms. And this is okay. It's okay that business logic leaks into these feature transforms because, like I said, we don't want different code being written for training and serving. So at least the business logic is coupled with the model, and that's okay. The only pain is that you have to work with your customers to develop these feature transforms. But this is the key enabler that makes model inference really fast. So in order to get the Python bindings, we collaborated with the MLeap developer team, and we've basically joined them. So I encourage you all to try out MLeap as well. And if you need any help, just open an issue on GitHub, and one of the folks on the team will help you try out MLeap. All right, so Rajvinder mentioned the tech stack and how we can deploy the model in different environments. So I want to cover a little bit about like the trade-offs of microservice versus search engine. So most of our ML models are deployed as a microservice, and you kind of think of this as like features are being sent to this through this API, and like a scoring or a classification is sent back. And this works fine for like only a few different entities being scored, and for small data, like predicting your wait time at a restaurant. For ranking all the businesses at Yelp, this doesn't make sense as an architecture, and so that's sort of the trade-off. The network I/O would be too high if we want to like rank all the businesses at Yelp. So instead, we wanted to deploy this model directly within a native search engine. Yelp uses NRT Search, which is our open source contribution that is similar to Elasticsearch. It runs on top of Lucene, and so it has documents like you may have heard of with Elasticsearch. And you can read about it on our engineering blog about like our decisions there on like how that project evolves. Our MLeap model inference package, and I should say like our wrapper around the model inference package that uses MLeap is portable to different JVM environments, and so it worked also within NRT Search for scoring the different businesses and then outputting a ranking of which businesses scored the highest using the ML model. Like I mentioned, NRT Search has documents. So the business features themselves of like which businesses need to be ranked for which search query are stored within the document themselves instead of having to send it over the network. And one other note about this is that like we actually had a huge product win by being able to increase our recall in the system by being able to rank all the businesses at Yelp instead of just the ones that could go over the wire to microservice through a microservice call and back. But embeddings are a key component of this, and so we had to work with the team that develops NRT search and add vector data type support to support those embeddings. All right, so I mentioned embeddings in model training, but like where do we want to do these embedding lookups in deployment? So there's three main options, and each of them makes sense in different scenarios. So the first one is store in the model binary itself, and this is fine for small things like the business category or which geography the business is in. We could store them in Cassandra, just for a lookup. This makes sense for things that are invariant with respect to the search. So like user embedding is a good example here. If the user has an embedding trained for them, we could look them up as part of the query and apply it to the model. Or NRT search documents is the third option. And this makes sense because we can store the business embedding for each business within the business document itself. Ideally, everything would just be in option one, the model binary, but it's too large for our use case of all the businesses at Yelp to be stored as part of the model binary. And just to clarify the point, like the idea behind options 2 and 3 is to reduce the model binary size for info requirements. And just to further motivate this, NRT search has a huge amount of info requirements because it's ranking businesses in real time and making sure that the search query executes super fast. And so we can't dedicate tens of gigabytes within the JVM heap to our application. As much as we want to promote ML ops, we need to be respectful of the deployment systems as well. So this is great. It all works, but it's too slow. So we had to play around with threading. NRT search, of course, as you can imagine, is multi-threaded because it needs to score business documents or documents at once. Tensorflow is also multi-threaded, which is great. Makes sense for most workflows, but it wasn't for our use case. We noticed that the latency was just too high for a good search user experience. You'll never get to the production of a new ML model if the end user experience is worse than the status quo. So one of the things we tried was to force TensorFlow to operate in a single-threaded fashion, while NRT search, which kicks off that thread, is still multi-threaded. We found that this avoids the resource contention for consecutive searches, and then the obvious point here is that it trades. You get lower throughput, but lower latency, which is what matters in this business use case. NRT search can scale up more instances if we want to counterbalance that trade-off of throughput. All right, I'm going to hand it off to Rajvinder to talk about some future work.
All right. Thank you so much, Ryan. Cool. So this slide essentially is where we're going to talk about the future of the ML platform. And to talk about the future of the ML platform probably makes sense to give a sense of where we're coming from and the progression over time. And so really, the platform started off with use case specific tools, and our customers felt very specific needs around deploying XGboost models to production, which has prompted the creation of the model server. There was customer pain around or developer toil around creating Spark ETL and data pipelines, which prompted the creation of the Spark ETL library and general ML compute requirements to support the ML workflows. As those tools grew in success within the company, there was a need for maybe end-to-end platformization. And really, the need to standardize key steps of the ML workflow is where we were potentially wrapping up this cycle, essentially, or this step of the ML platform's maturity. And so from a training perspective, we built the model trainer library to encompass the key ML libraries that folks were using to train their models, such as XGboost and Spark ML. and introducing the MLeap training and serving integration that Ryan just told us a lot about. And so these steps, like we talked about, are standardizing key workflows. And from a feature source perspective, we've also spent a lot of time standardizing our offline and online data stores into an internal centralized feature store. And this has enabled a lot of cross-functional, cross-team collaboration and sharing of ML features instead of the siloed pipeline jungles that might develop or that might have existed before. And lastly, we've been able to bring our ML compute to a modernized Kubernetes or cluster management tooling, which has allowed us to keep up to date with the industry innovation. But really where we're headed now is to this idea of a continuous learning system. And we want to move away from the idea of systems that produce models as artifacts and models being essentially the end product of this engineering toil. And really, we want to move towards an idea that the key revenue-generating ML systems in our company are more intelligent, and they're continuously learning. And so the key projects there are around incremental model training. As neural networks get more widely adopted, this reduces the cost to retrain your model. We want to build more automated deployment workflows, and so we want to have key revenue-generating ML systems and just key ML systems in general have the ability to be automatically deployed with a human in the loop in the process, but just generally reducing the manual steps involved in that process. And last but not least, we're building an internal advanced ML monitoring system, which is able to detect or notify an ML practitioner when the model that they're training or that they have trained is encountering a different feature distribution online that was trained offline, and potentially there's a need to retrain the model. These three projects are really the pillars behind these ideas of continuous learning systems, along with developing and standardizing other key steps in the ML workflow, such as standardizing hyperparameter optimization and TensorFlow support like we've been talking about. From a feature source perspective, I think a really interesting project that we're going to tackle in the near future is the idea that the feature stores, which are now centralized and standardized, there's potential to add more metadata in these systems. And so, for example, understanding where, like the data lineage aspect, where they're computed offline, and where these features need to be in an online environment for the models that they might serve. But more importantly, I think there's a lot of interest inside the company around integrating things like maybe in feature importance for one model to another. And so now that the feature is standardized, we really want to help ML practitioners choose features and prioritize these features based on their relative importance to other systems, such as search features being highly relevant to features in ads and things of that nature. And of course, we want to reduce developer toil. We want to essentially eliminate as many steps as possible between the construction of a feature in an offline batch way, and it's shipping it to the right data stores, such as NHT Search, like Ryan mentioned, or even Cassandra or other online data stores where that feature will be available for inference and production. And from an ML compute perspective, there's a couple more technical projects, but given the rise or given the more popularity of neural networks, we want to be able to leverage their potentially multi-GPU architectures, which means that we have to move our TensorFlow model training from the Spark driver, where it currently sits, back to the Spark executor, and potentially enable Kubernetes native workflows. And so we know that we're not going to be able to support every key ML library in our model trainer software interface. And so potentially we want to add an escape hatch for our customers to dive right into Kubernetes and deploy these large training jobs with libraries we might not support yet in a Dockerized, containerized DAG workflow using things like Argo. And I think lastly, the things that tie all this together from a goal-setting perspective and even from a business perspective is this idea of an MLOps maturity framework, which we've worked really hard internally to develop. And so this framework is based on the ML test score, which many people might have heard about. It's a pretty seminal paper in industry and academia research. But the idea is that internally we've iterated on this ML test score, and we've defined levels for different steps in the ML workflow. And this leveling really allows technical leads on different teams to provide a shared vocabulary and score the maturity of their ML projects at Yelp. This is very useful for us as an ML platform team because we can use that level to encourage people to invest and build technical roadmaps to get from, let's say, one level of maturity to another. And really, it also helps us as a platform team understand what infrastructure is most needed to get from one level of maturity to another. And so lastly, it motivates customers of our platform to adopt our latest tech, which we always want more customers as a platform team. And we want to ensure that we're adopting best practices as necessary so that we can deliver more business value for Yelp as a company. Cool. I'm going to hand it back to Ryan to wrap this up.
All right, I wanted to provide some resources for you all. These are the Yelp-based resources on like the engineering blog on when we introduced our model platform a couple years ago. But the ideas are still kind of foundational in how we think about all the things that Robert and I mentioned today, both in the NRT search that the talk was mostly focused on, but also our broader platform perspective. The second link is on our ranking platform system called NRT Search. If you didn't get the picture here, you can just go to Yelp Engineering blog and find it there as well. I also want to provide resources on MLeap and Spark ML and MLflow. These are some of our key components to the framework as well. And also point out some Yelp-wide resources. So we are very active on our engineering blog. All the blogs get posted to our Twitter. We also have a lot of open source projects on GitHub. I also want to call out, we have an awesome women in engineering group. Can't read it, it says awesome women in engineering, AWE. And so check out that as well. We are hiring. This picture was taken a while ago when, in the before times. And now we are a remote first company. Like I mentioned, where going into the office is strictly optional. All of our meetings are conducted in that fashion. So I wanted to clarify this picture and kind of the tweaks and how we've evolved over time. And I wanted to cover the different hiring areas real quick. So almost all the things we talked about today was in the ML platform area, spanning from like running Spark on top of Kubernetes, the ML ops framework that we covered, feature stores, observability, embeddings development, even supporting the applied ML research as well. Before I managed the ML platform team, I was actually an individual contributor on two of the teams mentioned above. First is in trust and safety. Basically, our core review recommendation algorithms are in part of trust. Yelp is the most trusted review website on the internet, and that's supporting the ML use cases there is really important. Also, content moderation, keeping the platform safe and as well. The other thing, in consumer engagement, we mentioned the popular dishes. There's a whole host of ML models that we worked on there where taking like review mining of predicting what the menu is based on the review text, and then taking the photos that are on Yelp and predicting what is in each photo, and then take the fuzzy matching of the photo caption to the menu item prediction, and then trying to figure out like which one of the popular dishes ranked highly in the reviews as well. And then zooming back out, there's a lot of work in the search models, business recommendations, the waitlist prediction that we mentioned. The other area that is really interesting is, and obviously very important for Yelp, is revenue intelligence. Yelp has it's basically its own advertiser marketplace. And so we have a lot of advertiser recommendation, ads models. Basically, we want to keep the ads marketplace healthy. That is both beneficial to our users and to our advertisers, and make sure we provide the most value to everyone. And the last slide, we are hiring, and here's how you can take your next steps, career at Yelp. The slide the picture on the left is basically we'll go to my recruiting team, more in the ML space. So even if you're in the ML modeling space, that would be the right one, and we can reroute you to the right rec. If you're more in management or just want to check out all the roles, that's what the other picture on the right goes to. That's all I had. Oh, I guess real quick, we're also going to be at the career fair at 4:30. So if you want to come ask us questions there, I guess we have a few minutes for questions, depending on.
First of all, it's really interesting to hear about how different companies have their tech stacks. Really cool to hear the tools you use. I'm also curious about how often you relearn your embeddings.
That's a really good question. We have explored this for a while, mostly for the recommendations use case. And what we've found is that we've often need to train our embeddings per business use case. That is evolving a little bit with these like foundation models, but historically we've had to sort of retrain the models per use case, and so that would often be like per quarter, that kind of thing. But where we'd like to be is use some of the incremental training that Rajvinder mentioned, where like, we have like all of the so how we train the embeddings in the first place is like biz views per user and use a sentence encoding. That's one of our kind of our main use case there. But like once we've trained that, we have new business views. We'd like to kind of incrementally retrain that instead of have to reapply it. So we'd like to do this regularly. So all the time is where we're going, but not all the time is where we're at now.
Yeah, that definitely makes sense. Thank you.
Hi. I was wondering, like, when you started supporting kind of like these deeper, more data-intensive models, was there a case where your data serving couldn't keep up? For example, like you suddenly support a super wide network, and now you have a use case for like a large language model embedding. Did you have problems with maybe serving these embeddings real time when you're trying to run these networks?
Yeah, so the latency is the issue, just so I understand the question. We found that using MLeap was the way to like reduce the timings. And one key component is where to store the embeddings. Let me go back. This is, I think, the closest slide that gets at the question. And I think for business embeddings, it's tens of gigabytes, and so we couldn't really store it in the model binary itself. That'd just be too slow. And so I think that's like the issue there. And so we actually split it up. Even though the embeddings of all the businesses at Yelp is tens of gigabytes, each business has a much smaller embedding for itself, and so we put that directly with the document. So actually splitting up the embeddings was probably the key enabler there. Does that get to your question?
Yeah, and I think just to add on to that, I think you had a question about large language models, but did you want to clarify?
Okay, I guess one step further, was there ever a point where it's not like technically feasible to serve something? What if you have an embedding that's like 1,000 or 2,000 long?
So I don't think it's the embedding size, like the dimensions and the embeddings that are the blocker here, as much as it is like some of the larger, deeper models that we're still figuring out how to serve, like these larger language models in production, and to what like there's like obviously techniques there to distill them or quantize them, but I don't think necessarily the embedding size has been a blocker, but for some of these more sparse embeddings, like we have found techniques to reduce dimensionality to increase inference speed there, but that's what Ryan mentioned in the talk, and I think there's other techniques that we probably didn't go into as much detail on, as it was a really iterative process with the applied scientists in our team to deploy this model.
Yeah, thank you. We can talk more too at the career fair.
Well, thank you again to Rajvinder and Ryan from Yelp, and check them out at the career fair at 4:30.